Welcome to the Depth Dive. Today we're getting into something really interesting, not just radar, but actually building uh, virtual radar systems right on your computer. So forget the hazards, forget the massive costs of real-world tests. We're going digital.
Exactly. Radar simulation, it lets us explore sensing tech in a truly agile way. Imagine just instantly tweaking parameters, testing these extreme scenarios that, might be dangerous or even impossible in reality. It really speeds up how we learn, how we develop these systems. It's about unlocking rapid innovation.
And a key tool for this virtual lab seems to be SensingSP. It's an open source Python library, right? Bringing electromagnetic sensing, including radar, to life in these detailed 3D scenes.
Yeah, and what's really fascinating, I think, is how SensingSP uses Blender. That integration, it allows for incredibly detailed visual scene building and, crucially, simulating how the radar signals actually behave, how they move through that virtual space. It sort of bridges the gap between how we see a scenario and the physics underneath. Wave propagation.
Okay, let's unpack that. So you can literally design your test setup visually in Blender, no coding needed. That's the add-on UI part. But then if you want to, dive deeper, automate things, there's also this powerful Python API. Sounds like you get choices depending on your comfort level.
Precisely. The Blender add-on, it's brilliant for quickly sketching out ideas, getting a visual feel, and it's great for anyone who prefers that intuitive graphical way of working. Then, for people doing serious research, running tons of simulations, maybe optimizing designs by sweeping through parameters or linking it with other analysis tools, well, the Python API gives you that essential full scripting power.
And they work together.
Yeah, they work hand in hand, seamlessly.
That's a huge plus. And I see it supports different radar modes too, like FMCW and MIMO. For listeners familiar with radar, that opens up simulating some pretty sophisticated systems, doesn't it?
It certainly does. SensingSP is really designed with education in mind, letting new engineers learn by doing. And for researchers, it lets them test novel ideas super quickly, get prototypes running virtually, way faster and cheaper than traditional methods.
Okay.
Now, to really get how these simulations are so realistic, we should probably touch on the core components involved.
Absolutely. Yeah, let's break that down.
Okay, so at its heart, a simulation in SensingSP has a few key pieces. First, you define your radar sensor. That sets the waveform where the transmitter and receiver are, things like that. Then you get your targets in the scene. These are the 3D objects, the surfaces that reflect signals, any obstacles.
Right.
And, crucially, the propagation model. This uses ray tracing to simulate how signals travel, accounting for, multiple paths, things getting blocked. And finally, the signal processing part takes that simulated raw data and turns it into the outputs you'd expect, like range plots.
Okay, so this propagation model, using ray tracing, that sounds like the secret sauce for realism. How does that work for radar exactly? It's not just like light, is it?
Well, it's similar in principle. Think of how light rays travel. Radar signals, being electromagnetic waves, travel similarly. Ray tracing models these signals as rays starting from the radar, moving through the virtual scene, interacting with objects. So it calculates the direct path, sure, but also, and this is key, indirect paths, where the signal bounces off, say, a wall before hitting the target or coming back. That's multipath.
Okay.
And it figures out if anything's blocking the direct path occlusion. It even considers how different materials affect the reflections.
So ray tracing lets SensingSP mimic those real-world headaches, like a signal bouncing off a building before hitting a car, or just being blocked entirely by something. That sounds vital for testing how well a system actually performs when things aren't perfect, which, let's be honest, is always the case.
Exactly right. It's essential for developing algorithms that can handle that real-world messiness and for, stress testing your system against tricky edge cases. And SensingSP actually gives you 3 different levels of ray tracing fidelity. So you can choose the right balance between accuracy and, speed.
3 modes. Okay, interesting. Give us the rundown.
So the first is light mode, fastest but simplest. It only looks at the direct line of sight. No reflections, no occlusions. Think of it as just seeing the most obvious path. Great for quick initial tests, maybe really huge scenes where speed matters most, or if you're just starting out.
Right. Get a quick, basic picture without getting bogged down in environmental details. What's the next step up?
That's balanced mode. This one offers a really good trade-off, I think. It calculates the direct line of sight, but importantly, it does check if something's blocking that path, so you get occlusion.
Shadows, basically.
Exactly, shadows. But it doesn't simulate the full complexity of all the multipath reflections.
Yeah.
It's a solid choice for most situations where you need that extra realism from blockages, but maybe don't need every single possible bounce model.
So you get that crucial shadowing effect, which is a big deal for real radar. And then the third mode is everything, full complexity.
Precisely. Advanced mode. This uses the full power of ray tracing. Multiple reflections, maximum realism. It's the go-to for deep research where those subtle interactions, signals bouncing off several surfaces are really critical to understand. And within this mode, you also control something called the bounce number.
Bounce number. Does that mean how many times a signal can reflect before you stop tracking it?
You got it. It lets you set the maximum number of reflections the simulation will model for a single ray. And naturally, the higher the number, the more complex the calculation, the longer it takes. So it's a balance, capturing fine details versus keeping simulation times reasonable. And it's worth remembering, too, that the complexity of your 3D scene itself really matters. More detail means more ray tracing calculations.
Good point. Keep the virtual environment focused on what's actually important for the simulation to stay efficient. Okay, we know what these modes are, why they matter. How do you actually, pick one in SensingSP?
Oh, it's designed to be pretty straightforward. If you're using the Blender add-on, the UI, you just click your choice in the Sensing Signal Processing panel. Easy. If you're scripting with the Python API, there are specific functions. Set ray tracing balance for balanced, set ray tracing light for light mode,
And advanced.
and set ray tracing advanced intense for that full multi-path simulation. So visual or code, you've got direct control.
That flexibility sounds great.
Yeah.
Now let's switch gears slightly to the practical side. Running these simulations, we've mentioned the Blender UI and the Python API. Can you talk more about the strengths of each? Who uses which and why?
Absolutely. So the Blender add-on UI, its big advantage is no coding needed. You interact visually right inside Blender. That makes it perfect for people new to simulation, or maybe new to programming. Great for quickly visualizing a scenario, testing basic ideas, getting that immediate visual feedback. Think of it as like a rapid prototyping space.
Okay, so visual learners, quick concept checks, the UI is the way to go. What about the Python API then? When does that become the better choice?
The Python API, which you'd use in something like VS Code or maybe a Jupyter notebook, gives you, well, complete programmatic control over everything. This is where you unlock the advanced stuff, essential for research where you need automation, running big batches of simulations with different parameters, maybe doing parameter sweeps to optimize a design.
Like finding the best settings?
Exactly.
Yep.
Or integrating the results with other data analysis tools, maybe even training machine learning models. The API is key for that level of rigor and customization.
So API for the serious, repeatable, highly customized stuff. But what if you start visually in Blender, then realize, oh, I actually need to script this now?
That's where the integration really shines. You can design your scene, set up your initial radar stuff in the Blender UI, then you can export or save those settings, and then use the Python API to load them and take over with scripting. Automate runs, vary parameters programmatically, do complex analysis, all based on that visually designed scene. It's a pretty smooth workflow.
Nice. So you can move between visual design and code-driven analysis pretty easily.
Yeah.
Any best practices you'd recommend for someone starting out wanting to leverage both?
Yeah, I'd definitely say start with the UI, get a quick visual feel, prototype your basic setup. It's great for visual debugging too. But for anything beyond those initial explorations, especially if you need reproducibility, automation, fine control, definitely transition to scripting with the API. It also makes collaboration easier, right? You can share .blend files for the visual setup or share Python scripts for the full simulation pipeline. Caters to different styles.
That sounds very practical. Okay, for someone listening who's now eager to try SensingSP, what's the install process look like? Is it complicated?
Good question. There are guides online, detailed ones, including a specific one for the Blender add-on on Windows, which came out, I think, December 2024. Generally, though, it involves installing a few key pieces of software.
Okay, walk us through the basics. What do people need?
Right. First, you need Blender itself, version 4.0. You can grab that from the Blender website. Then you need Python 3.1s installed. SensingSP relies on that specific version. For Windows users, you might also need the Microsoft Visual C++ build tools, sometimes needed for compiling Python bits, helps avoid installation hiccups.
Okay.
After that, there's a Python library called MathTools, essential for Blender's 3D math stuff. You install that using pip. Pip install MathTools.
Got it. Blender 4.0, Python 3.0, maybe build tools, then MathTools. What's next?
Next is the main SensingSP package itself. Again, use pip.pip install SensingSP. You can find the latest version usually linked from their GitHub page. Once that's installed, it's smart to just quickly check it. Open a terminal and run this Python command, python-c, import SensingSP print, SensingSP version. If it imports and prints a version number with no errors, the Python side is good to go.
Excellent. So the underlying Python stuff is ready. How do we connect it to Blender then?
Right, the final step is installing the add-on inside Blender 4.0. Open Blender, go to Edit-Preferences, find the Add-ons tab, click Install the IP. Then you browse to wherever you downloaded the SensingSP add-on.zip file, again, probably from their GitHub. Select that .zip file, click Install Add-on. It should then appear in the list, probably as Object Sensing Signal Processing. Just check the box next to it to enable it, close Preferences, and you should be set. The tool should appear in Blender's UI.
Okay, sounds manageable. So once it's all installed and running, what kind of output would we see from say, a simple first simulation?
Yeah, you typically see a few things. In Blender's 3D view, you'll see your scene, your targets, the radar model. And SensingSP generates the radar data. So you might get plots of the raw ADC samples, the digitized received signal over time. You'll likely see a range FFT plot. The fast Fourier transform helps pull out frequencies, which tells us the distance, the range to targets.
Yeah.
And often a range Doppler plot, too. That shows range and velocity relative to the radar. There might even be a sample file included, maybe called something like manflatfall.blend, that have a whole scenario ready to run so you can see these outputs right away.
That combo, the 3D visual and the data plot, sounds incredibly helpful for actually understanding what the simulation is doing. Now, I saw a mention of SensingSP. What's that about?
Yeah. The idea for SensingSP is basically to be a central online spot for the SensingSP community. A place for tutorials, example simulations, code snippets, maybe a forum for users to connect, ask questions, share what they're doing, build a community around it.
That sounds like a great resource, especially for helping new users get started. Okay, let's shift back a bit to radar fundamentals. The outline has some really key questions. Let's start with the most basic. How does a radar actually figure out the distance to something?
Right. Fundamental stuff. It's all about time. The radar sends out a pulse of electromagnetic energy. It travels to the object, reflects off it, and travels back. The radar precisely measures the time that round trip takes. Since we know the speed of light, that's how fast the signal travels, we can calculate the distance. If the distance is d, the signal travels taken. So the range d is just half the travel time multiplied by the speed of light. Simple as that in principle.
Makes sense for one target. What if there are multiple objects out there at different distances? How does it tell them apart?
Good question. If you have multiple objects, say at distances d1 and d2, the radar gets back multiple reflected signals, or echoes. Each echo arrives back at a slightly different time, corresponding to its distance. By processing these returning signals, the radar can usually distinguish these separate echoes and figure out the range to each object. The real challenge comes when objects are very close together.
Oh, which leads perfectly to the next question. How close can two objects be before the radar just sees them as one big blob?
Yeah, this is all about range resolution. A radar's ability to separate two closely spaced targets depends mainly on the bandwidth of the signal it transmits.
Bandwidth, like the range of frequencies it uses.
Exactly. A wider bandwidth generally means better or finer range resolution. It can distinguish objects that are closer together. If two objects are closer than the radar's range resolution limit, they'll probably just look like one larger echo. So if you have objects at d and plus tris, the radar can tell them apart only if their separation is at least tris, the range resolution.
Okay, so wider frequency range equals sharper vision in terms of distance. Now, what about the other end? How far can a radar see? What limits its maximum range?
The maximum range, often called Dmax, is determined by a bunch of factors. It's all wrapped up in the radar range equation. Key things are how much power the radar transmits, how well its antennas focus that power, antenna gain, how big the target appears to the radar, its radar cross-section, the signal's wavelength, also any signal losses in the system or atmosphere, and crucially, how weak a signal the receiver can detect above the background noise, the minimum detectable signal or signal-to-noise ratio.
So power, antennas, target size, receiver sensitivity, it's a mix.
Yeah. Think of it like shouting across a noisy canyon and listening for the echo. You need a loud shout, a good reflecting surface, and really good hearing to pick up the faint return.
That's a great analogy. Now, we talked about range resolution. Can we visualize what that looks like in the actual radar data?
Sure. Imagine the radar sees two objects. One's at, say, 3 meters, the other's at 5 meters. If the radar's range resolution is good enough, when we look at the process data, specifically that range FFT plot we mentioned, We should see two distinct peaks. One peak lines up with 3 meters, the other with 5 meters. The sharper and more separate those peaks are, the better the resolution. If the objects were super close, maybe just centimeters apart, those peaks might merge into one broad hump. Then it's hard to tell if it's one target or two.
That visual of separate peaks really helps clarify range resolution. Okay, let's dive into a specific signal type often used, the chirp. What exactly is a chirp signal in radar?
Right, a chirp in radar is basically a signal where the frequency changes over time. A really common type is the linear frequency modulated continuous wave, or FMCW chirp. In FMCW, the frequency usually increases linearly, like a ramp over a set period. Sometimes it decreases, but linear increase is common.
And why use a chirp? What's the advantage over just sending out a single constant frequency?
Chirps are clever. Especially in FMCW radar, they let you achieve high range resolution and measure velocity using the Doppler effect, all while using relatively low transmit power. It's an efficient way to pack a lot of measurement capability into the signal.
Interesting. So how does this frequency change actually happen? Can you give us an example?
Okay, imagine a radar sends out a chirp starting at 77 gigahertz.
Yeah.
Over, say, 40 microseconds, that's the chirp duration. TC, the frequency ramps up linearly to 81 gigahertz.
Oh.
So the total frequency change, the bandwidth B, is 81 minus 77, which is 4 gigahertz.
Okay.
We can also talk about the chirp slope S,
Yeah.
which is how fast the frequency changes. That's just the bandwidth divided by the chirp time.
Yeah.
So 4 gigahertz divided by 40 microseconds.
That's 4 billion hertz divided by 40 millionths of a second. A very fast ramp.
It is. Now, the signal that comes back, its phase holds the key information about range and velocity. For an FMCW chirp, the phase of that returning signal is directly tied to the chirp parameters, the slope, duration, and the round-trip travel time to the target. There's a specific mathematical relationship there.
Okay, so the changing frequency encodes the information. Can we see how SensingSP generates these chirps in the simulation?
Absolutely. SensingSP has tools for this. For instance, there's a Python function, something like ssp.radar.waveforms.generate FMCW signal. You'd feed it parameters like the center frequency, F0, maybe 77 gigahertz, the bandwidth, B, 4 gigahertz, the chirp time, T, 40 microseconds, and the sampling rate you need.
And what would that simulated chirp look like if we plotted it?
Well, if you plotted the raw signal versus time, you'd see its amplitude. Maybe its real and imaginary parts oscillate very quickly, but more revealing is the spectrogram that visualizes frequency versus time. For our chirp example, you'd see a clear diagonal line starting at 77 gigahertz and rising to 81 gigahertz over that 40 microsecond window.
Okay.
And if you looked at the frequency spectrum of the whole chirp, you'd see its energy spread across that entire 4 gigahertz bandwidth.
The spectrogram really shows that frequency sweep clearly. Now, the outline mentioned an FMCW chirp parameters calculator. What's that for?
That's a super useful tool for designers. It helps you figure out the chirp parameters you need to achieve the performance you want. You basically tell it things like, what range resolution do I need? How many ADC samples will I take per chirp? What's the maximum time I can allow for one chirp? What velocity resolution do I need? What's my center frequency?
So you input your requirements.
Exactly.
Yep.
And based on those inputs, it calculates the necessary FMCW bandwidth, the ADC sampling rate required, the resulting chirp slope, the maximum range you'll likely achieve, and the velocity resolution. It might also flag constraints like how many pulses you need for a certain velocity accuracy.
So it works backward from the desired performance to the signal specs. Can you give an example? Like plug in some numbers.
Sure. Let's say you need a range resolution of 0.03747 meters. You plan to use 256 ADC samples. Your max chirp time is 40 microseconds, and the central frequency is 79 gigahertz. The calculator might then tell you, okay, you need an FMCW bandwidth of 4.7 gigahertz. Your ADC needs to sample at 6.40 megasamples per second. Your chirp slope will be 100.01 megahertz per microsecond. It might also estimate your max range at, say, 9.59 meters and your radial velocity resolution at 0.13 meters per second.
Okay.
And it can show trade-offs. Like if you dropped to 128 ADC samples but kept the 40 microsecond chirp time, the required ADC sampling rate would drop to 3.2 megahertz.
That's incredibly useful for understanding the design trade-offs, how changing one thing impacts everything else.
Wow, well, this has been a really fascinating deep dive into radar simulation with SensingSP. It sounds like just an invaluable tool for anyone wanting to explore or innovate in radar without the usual hardware headaches and costs. Absolutely. That mix of the user-friendly Blender side and the powerful Python API makes it really accessible. For students learning the ropes, right up to researchers pushing the limits, being able to create these realistic virtual sensing worlds, it just opens up so many possibilities for education, for rapid prototyping, for really digging into complex radar system behavior.
It really does make you appreciate how these virtual tools can accelerate radar development and deepen our understanding of sensing. If what you've heard today sparked your interest, definitely check out SensingSP for your own projects or just for learning. You might be surprised what virtual scenarios you can build and what you can discover. Thanks for joining us on this deep dive.